Hey, this is Dr. Cofield. This is the last part of chemical equilibrium. And so in this part, we're continuing our discussion of LeChatlier and how equilibrium reactions restore equilibrium depending on the disturbance. And in this part, we're going to look at the effect of temperature change on equilibrium. And then we're going to look at general effects of disturbing equilibrium, like adding catalysts and such as that. And then I'll give a little overview of LeChatlier changes so you can kind of see how each one fits in. So as we said, LeChatlier says whatever effect you do, you're going to try to work against that, okay? So when it comes to temperature, some people look at this and think that it's more complicated than the other changes, but it's really not. The prediction is that the effect of temperature, even though heat's not matter, it can be written in your equation different ways, but you look at it as if it is a product or a reactant. And then you do the push me, pull me like we were talking about in chapter 7. Okay, so the things you remember is if it's exothermic, okay, it releases heat. So heat is a product. And so another way of saying exothermic is a negative delta H, right? And so if it's a negative delta H, it also means that heat is a product. So you can either write it A plus B equals C plus D plus heat. Okay, that means that's exothermic and heat is a product. Or you could leave, if you leave that out and say the delta H is a negative 84.3 kilojoules. Okay, that's another way of saying it's exothermic and it would be a product. So you just got to remember those go together. Exothermic, heat is a product. You quantify that by putting delta H is a negative number. Okay, and so heat is a product in either one of those cases. So either way that you write that reaction, you got to remember that. The opposite is true with an endothermic. Endothermic absorbs energy, so it's going to have a positive delta H, or it's going to be written as a reactant. Okay, so if it's an endothermic, it's a reactant, and so you still look at it in terms of, are you adding or are you releasing? If you heat something up, you're adding heat. If I'm adding heat and it's endothermic, I'm going to push it to the right. If I put it in an ice bath, I'm removing heat, so I'm going to pull it to the left. Okay? So think about that for a minute. It's very, very simple when you think of it in those terms. So, and that's what this slide is for, so you can read that at your leisure. I don't like reading slides to people. But if you remove something, you're going to pull it towards what you removed. Okay, so you're pulling it towards that. If you add something, then you're adding it and you're pushing it. Okay, so same thing with heat. And so this is just like a little visual for those of you visual people like me. If you're at equilibrium, you're balanced. Okay, if you disturb the balance where you add some reactant, in order to get back to equilibrium, you have to move away from that. So you have to get it back balanced. And then by doing that, you get balanced again and reestablish that equilibrium. So whether it's heat or whether it is a concentration, it all works the same way. All right, so we've seen this one before. CaCO3 solid plus CaO solid gives you CO2 gas. What's the effect of increasing the temperature of the reaction mixture? Now, I need to know something. What? It's endothermic. There it is. It's endothermic, which means what? It means that heat is a reactant. So I'm going to go ahead and write it in there so I remember. It's a reactant, so heat plus CaCO3 gives me those things. So if I increase the temperature, I'm adding heat. If I'm adding heat, then it's going to do what? It's going to push it to the right. If I decrease the temperature, I'm removing heat. I'm going to pull it to the left. This one's exothermic, which means heat is a product. If I increase the temperature, I'm increasing temperature, I'm going to push it to the left. If I decrease the temperature, I'm going to remove heat, pull it to the right. Same as if I was adding concentration. Okay, so this is a good thing to kind of review these, okay? So we've got this reaction here. We have different factors to look at, and we're going to see what is the reaction, or what is the effect on the reaction of each thing that we do. All right, so first I'm going to evaluate this because I need to know stuff about how many moles of, well, I won't have to do that until the next one. All right, so if it was going to ask me gas things like pressure, oh, it does ask me some pressure stuff, right? Decreasing the volume. So I'm going to look and see how many moles of gas I got on both sides first. So I've got 2 moles of gas on this side, and I've got 3 plus 1, so that's 4 moles on this side. Well, I'm doing that because if it's a pressure volume thing, I've got to remember how that works, right? All right, and then it's a negative 92 kilojoules, which means that it's exothermic, which means heat is a product. Now, once I figure that out, okay, then when I look and see what I'm doing, I'll be able to either push it or pull it. All right, so increase the reaction temperature. So if I increase temperature, I'm pushing heat, so I'm pushing to the left. If I decrease it, I'm pulling it to the right because I'm removing heat. If I increase the pressure by decreasing the volume, it's going to go to the right. Why? Because if I increase the pressure, it's going to go to the side with the least number of gas moles. If I increase the temperature of the hydrogen, okay, so I add that, it's going to push it to the right. If I decrease the ammonia, I'm going to pull it to the right. If I add a catalyst, what's it going to do? It will not change the equilibrium. It will change the rate, okay, but it will not change the positioning of the equilibrium because it affects everything the same way. All right, let's look at this second group. All right, H2 plus I2 gives me 2HI, and it wants to know if I change the temperature, right? No, if I increase the pressure, okay, so I'm increasing the pressure on all of these. How will that affect the equilibrium in each one? Okay, so in this one I've got 2 moles of gas and 2 moles of gas. So if I change the pressure, it's not going to do anything because I have the same number on both sides, so there would be no effect on that one. On this one, I have 10 moles of gas on that side and 9 moles on the reactant side. So if I increase the pressure, it's going to the side with the lowest number of moles of gas, so that would be left. The next one, I have 2 moles on this side and 1 mole on that side, so it's going to go to the right, because remember I'm increasing pressure on each one of these, so it's going to go to the side with the least number of moles. This last one, I've got 2 here and 3 here. Now I was nice to you on these and I gave them all gases, right? But if some of those were solids or whatever, remember you don't count them. So I've got 3 on the reactant side and 2 on the product side, so it's going to be product favored. It's going to go to the right. On these, I'm going to increase the temperature. Increase the temperature. So I have to evaluate, are they exo or endo? Okay. Delta H0 is less than 1. Okay, that means it's negative. Okay, so that means it's exo. So that means it's a product. Alright, so I'm increasing the temperature. So if I increase the temperature, I'm adding heat. So I'm adding heat from the product side, so I am shifting it to the left. If I have, it's a positive, oh, it's adding, okay, it's adding 92 kilojoules, so that is a product. Got to be really careful. Okay, so that's XO. So it's plus heat. So if I'm increasing the temperature again, what am I doing? It's a product. I'm increasing the temperature, so I'm pushing that to, wait, make sure what I'm doing. Oh, endo. Oh, it's about to mess up. I knew I kept looking at it and it wasn't right. Endo means that the heat's on this side. Huh. I'm getting tired. I've done all 8 of these in one day. Whoa. So adding heat to the reactant side, and so that's going to shift that to the right, because if I add heat, I'm adding it from that side. This last one, the delta H, is a positive 25, which also means it's endo. Okay, and so endo means that it is going to be heat on this side, and that means that it goes to the right. All right, I don't know about this middle one. I'm still looking at it. No, I was right the first time. I shouldn't have doubted myself. Sorry about that. I hate to confuse y'all. Because it says plus 92 kilojoules, which means it is a product. So if I'm adding from the product side, so that means it's going to shift to the left. I apologize. Because it's written as plus 92 kilojoules, that means it is already written as a product. The delta H is a positive, means that it's an endothermic, which means that the heat is a reactant. Alright, so I gave you several different ways to look at that, so hopefully you can go back, and except for that one that I kind of messed up, you'll be able to go back and figure those out. So the last thing I'm going to talk about briefly is the effect of catalyst, and just remember that it's not going to affect the position of the equilibrium. It will only make it get to equilibrium faster, because it works the same way in the forward and the reverse reaction. So it's not favoring one over the other, therefore it speeds them both up, and so they get to equilibrium quicker. So, but if you're asked about the effect of a catalyst, there is no effect. And that is the end of this part, and that is the end of chapter 15 over chemical equilibrium. Yay!